Hey guys, welcome to SurviveIB. This is actually a continuation of the last lesson. I found an extra concept that might be useful, so this is Physics, Momentum, and Impulse, Part 2. And so, before we go on, we're just going to take a quick review of what we were working on last time, which was Newton's second law. And Newton's second law was the rate of change of linear momentum of an object is directly proportional to the net external force impressed upon it. And assuming mass is constant, that's what we did yesterday. Assuming mass is constant, we came out with the equation, the sum of the forces equals mass times acceleration. And so the one different thing we're doing today is, since momentum equals mass times velocity, that's momentum, and yesterday, the change in momentum was mass times delta v, the change in velocity, because we were assuming mass was constant. Well, you might realize there's another way to change momentum, and that is we can change momentum by changing our mass and keeping v constant. And that's what we're going to do tonight. We're actually going to change our equation around a little bit. This was our old equation. That's the sum of the forces equals mass times change of velocity over change in time, which is acceleration. This time, it's just an easy switch. We can just swap them around here. Our new equation for today will be the sum of the forces equals velocity times the change in mass over the change in time. And that's the equation we're going to be looking at in these problems, and let's get right to it. We got our first problem here, which is mass falls at a constant rate onto a conveyor belt, which is moving horizontally at 2.5 meters per second. If you want no more than 0.12 newtons of force on the conveyor belt, at what rate can mass be dropped on it? And so, first off, let's define some variables here. We know that the velocity of our conveyor belt is going to equal 2.5 meters per second. And we're going to know that the sum of our forces here is going to equal 0.12 newtons. And we know what we're looking for here. We know at which rate can mass be dropped on it. We know we are looking for the change in mass. And let's write down our equation here. Our equation is the sum of the forces equals velocity times the change in mass over the change in time. And you might notice one problem with this. The one problem is time right here. What's up with that? We might be missing another variable, you might think. Well, actually, the time interval is actually irrelevant to this equation. It was relevant to our old equation, which was the sum of the forces equals mass times acceleration, because you needed the time interval to find the acceleration, because you needed that there. And if you're still doubting, we can take a look at the graphs here. We got time. This is time. Time's really not going anywhere. It's remaining constant, unless you're some sort of time traveler. Here's our velocity graph, like that. That's velocity. And we'll use green here for our change in mass. That's just going to be a straight line. And the thing here is, so we're going to change the time interval here. So here's our first time interval, just right between here and here. Up, 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 up. And we'll take a look. So this is our mass and this is our velocity. And if you look at them, then you might think, well, these are actually, the slopes of these lines are actually pretty constant. They're not changing or going up or down. They look kind of, straight. The lines are straight. The mass line is totally straight, and even though the velocity line is curved, right here it looks pretty good. However, if we change this interval here, if we if we change the interval, which is delta t, that's what it's there for, we change the interval to all the way out here, suddenly we see a big difference. So the mass line looks fine because it's a linear function. It's just point A, point B, and connect the dots. It's not the slope here is not changing. It's always constant. However, on our velocity graph, we do see this sudden spike in the slope right around here. Suddenly it's going pretty constantly, but then boom, it goes up. And since we change the time interval here, that's going to take effect on the rest of our equation. That is why in this equation, which we are not doing right now, you have to consider the time interval. But in this one, since it's a one slope here, no change in the slope, you don't have to consider the time interval. So that actually allows us to change our variable right here. This isn't actually just the change of mass. This represents the change of mass and the change in time because this is irrelevant. This doesn't really matter. So this makes our problem actually really easy. We can just plug in our variables here and we get 0.12 newtons equals 2.5 meters per second times x, whatever our variable here is. And so how we do that, we're just going to divide both sides by 2.5 meters per second. That cancels out there, and we can see that 0.12 newtons divided by 2.5 seconds, that's going to equal 0.048 times whatever this is. So this is in kilograms, and actually this is time over here. So remember, delta t down here, that's in seconds. So kilograms divided by second is what we're going to do, kilograms per second. And actually, that is our answer. Forty-eight thousandths of a kilogram per second. Awesome. Okay, so let's move on to the second problem. Using the same conveyor belt design, as you can see, the power generator right there. Mass falls at a rate of 0.050 kilograms per second, so that is 50 hundredths of a kilogram per second, onto a conveyor belt which moves at a constant speed of 1.25 meters per second. What average force must be exerted on the belt to make it turn at a constant speed? So let's get our variables defined here, and in this one we actually do have the change in mass over the change in time, and that is 0.050 kilograms per second. And we also have our velocity of our conveyor belt, which is 1.25 meters per second. Actually, in both of these problems, we know that the change of velocity equals 0 because remember, it's going at a constant speed, so it's not changing. And what we're looking for in our equation is the sum of the forces. What is our sum? The sum of our forces, the average force we're looking for. And so once again, our equation is the sum of the forces equals velocity times the change in mass over the change in time. And since we already worked out the time problem, all we have to do really is plug it in and multiply. And so we can say that the sum of the forces equals 1.25 meters per second times 0.05 kilograms per second. Sorry about hit the edge there. But nonetheless, we can just put this in our calculator. It's a really easy problem. once we've kind of gotten through that time issue. So 1.25 times 0.05 equals 0.0625 kilograms times meters per second squared. And as you guys probably know, a kilogram times a meter and divided by a second squared, that is the definition of a Newton. And since we're working in 3 sig figs here, because that is our lowest number here, 1.25 is the restrictor, we can say that 0.063 newtons is our answer.